Hi, for anyone who doesn't know me, I'm Ben Sachs. My company, Sachs & Associates, offers training in C and C++ programming with a focus on embedded systems for companies all over the world. Got quite a lot to get to here, so let's just go ahead and do it. That said, if you do have any questions, I will do my best to answer them. Okay, so generally speaking, when we are writing embedded applications, we have some target hardware in mind. And obviously, the code we're writing needs to work on that hardware. But developing for the real hardware isn't always easy to do. There are costs involved in that. For example, generally takes time to upload code to the hardware. Sometimes we have limited debugging tools available when we're running on real hardware. And so if we can mitigate those costs a little bit by creating a simulated environment, that can improve our development time. So that's what we're going to be talking about doing in this talk. I'm using an example program that runs on the ARM Evaluator 7T. It's a pretty simple program. It just reads data from a serial port, one character at a time, and shows that character on a 7-segment display. I have a picture of this coming up in just a moment. So we're going to start out by making the program work on real hardware, and then we'll see how we can also make it work in a simulated environment on a typical desktop application. And when we're done, the code will be the same down to the point where we're accessing the individual hardware registers. But what we'll be doing is in the simulated environment, I'll be using operator overloading to reproduce the side effects that typically occur when we use hardware registers to produce similar effects in software. So here is a picture of the top half of the board that I was using for this. You can see we've got a couple of serial ports and our 7-segment display there. And there are other hardware devices on this, but those are the ones we'll be using now. Okay, so I'm going to have two primary objects in my program. UART0 is a pointer to an object of type UART, where UART is a class type that represents a serial port, and display, which is going to be a pointer to an object of type 7-segment display. Now I'm going to be focusing on the UART object in this talk because that's the one that's a little bit more complex, and so it demonstrates these principles and what we can do a little more effectively. But the 7-segment display, the simulation uses essentially the same techniques. So here is most of our example program. As you can see, it's pretty simple. Creates the objects for the UART0 and display, and I'll talk about how we do that in just a moment. But after that, it just loops forever, tries to read a character in from the serial port. If it can, displays that character on the 7-segment display. So before we dive into creating those objects, just a little bit more detail here. The get function on the UART is modeled on the iStream get function, tries to read in a character from the UART into the argument C. If there's a character to read, goes ahead, puts that character in C and returns true. Otherwise, just returns false. For the display, the put function just shows the character on the 7-segment display. Now, a 7-segment display can't quite handle the entire English alphabet. There are a few characters like X and W that are hard to display, but for the purposes of this discussion, I'm going to say close enough. Now, there are lots of ways that we could write these class interfaces. I'm going to be using a version based on the techniques that Dan Sachs covered in his talk memory mapped devices as objects at CppCon 2020. But the focus here is really on this use of operator overloading to create these simulations of hardware registers. And this technique can be adapted to other ways that we might create class interfaces for our device, for our hardware devices. So first, let's go ahead and get these working on the target hardware. So just a little bit of background here to make sure we're all on the same page. So CPUs typically communicate with hardware. And when I say external hardware here, that can still be on the board just outside the CPU via hardware device registers. And the device register is some piece of circuitry that provides an interface to the device. On the E7T, like on most modern hardware, these device registers are memory mapped. So each one of these registers has an address in memory space, and we can and so our memory space is going to look something like this, where we've got a section for our physical memory, and then another section elsewhere that's been reserved for speaking to memory-mapped device registers. And if we know the address at which a memory-mapped register is located, we can set up an appropriate pointer to that location, and then we can talk to that register as if it were just an ordinary object in C++. So here, I'm setting up a pointer that will point to the line control register of UART 0. I could similarly use a reference. Either one will work. Now, most devices that we have are going to be comprised of multiple hardware registers. So the UARTs, in this case, the serial ports, have 6 device registers. There are a couple of control registers, first off, used for configuring the device. There's a status register that gives us feedback about what's currently going on the device. We have buffers for holding the character to be transmitted and the character that was just received but hasn't been read out yet, and then a register that controls the baud rate. Since these registers are all located together in a clump like this, rather than access those registers individually, I'm going to group them up into this UART class here. So the data members of my class are going to be my device registers. And then I will have what looks like a typical class interface for interacting with that device, for creating my UART, reading characters out of it, etc. So to dive into this in a little bit more detail, the UART's constructor has 3 steps. It first disables the UART. It sets the baud rate to whatever the user specified, and then it goes ahead and re-enables the UART, and here I've set it to enable it for both transmitting and receiving, although we're really only going to be talking about receiving in this talk. So the code looks something like this. Not very complicated, although that said, I think that we can make this code a little bit clearer if we go ahead and introduce a couple of inline functions so that the disable, and enable steps. Now, there's no additional overhead because these are inline functions, but they're clearly called out as what exactly they're doing in terms of operating on the UART. Now, as I said, hardware operations typically involve multiple device registers. Oops. So, for example, when we want to read a character from the UART, when we're receiving data in from the outside world, the hardware stores that character in the receive buffer register, just one character at a time as they come in. And when it does that, it also sets a bit called the receive data ready bit, or RDR, in the status register for the UART. So we only want to read from the receive buffer when the RDR bit is set. Technically, we can read it from at other times, we just won't get anything meaningful. If we read from the receive buffer, that automatically has the side effect of clearing the RDR bit in the status register, sending the hardware back into a state where it can now go ahead and start receiving the next character. So here is the body of my UART get function here. I've highlighted the couple of places where I'm accessing the registers. So I go ahead, check for the RDR bit in the status register. If that's not set, no character to read, just return false. Otherwise, go ahead and read the character. That will automatically update the status register. And I can return true. Now, it's not that complicated, but it's non-trivial. It's not hard to imagine other pieces of code that would do similar tasks that might be more complicated than this. So we'd like to be able, remember, our eventual goal is to get to the point where this code, which is currently I'm talking about how it affects the target hardware, but we'd also like to be able to run it on our simulated hardware. That's where we're going here. Now, but back to the target hardware first off. The hardware has these specific memory locations that are carved out for the UART's device registers. So this function will only work correctly if the data members of the UART really are aligned to those memory addresses. And when we access those data members, we're really talking to those specific memory addresses. So we need a way of positioning the UART object in that appropriate space. And I'm going to do that using a special form of the new operator. This is not a version that allocates memory, so don't worry about that. New is being used here primarily because it helps us run the constructor the way that we'd like. So a little bit of background, a typical new expression, and here I'm talking about a typical use of new that would be allocating dynamic memory, but just as background, looks like this. What it actually translates into is something kind of like this. It's actually a two-step process where the first part is to call a function called operator new, specify the size of the object that we're asking for memory for as a parameter. Operator new will return back a pointer to some block of memory that's large enough to hold the object that we want to place there. And then we can go ahead and actually construct the object in that memory by running the constructor. Now that second line there is imaginary syntax for run a constructor at this location. You can't actually write it in C++, but that's just to give you some idea of what the compiler might be generating behind the scenes. Now, it turns out there's a way that we can make operator new do specific things for specific classes in C++. We can write operator new as a class member of a specific class. And when I do that, if T has an operator new function, then the same new expression instead translates into this. Very similar looking, but notice it's calling the operator new that's a member of T here. So it's fetching memory not from the ordinary free store heap, but from wherever that function tells it to get that memory from. And this only applies to objects of type T. All other objects in the program will continue to use the normal global operator new in this case. But we can write our operator new function in this case, so it doesn't actually allocate memory. It can specify a location that's not part of the free store. Again, what a lot of people call the heap. And in this case, we're going to write it so that it just always returns the address where UART objects belong. There's one place in the hardware where UARTs have to go to be meaningful for the hardware. Operator new just always returns that address. Actually, I guess I should say there are two places because we have two serial ports. But for this, to keep this code simple, I'm just showing you the code assuming that we're talking specifically to the first serial port. And then our 7-segment display is going to have a similar operator new function that just always returns the address at which the 7-segment display hardware is located. Now, a class that has a member operator new should also have a member operator delete, because if it doesn't, then if we ever try to delete the pointer, we'll wind up calling the global operator delete, which will assume that we got our memory from the global operator new, which we didn't. We didn't really allocate memory at all. And so in this case, since we didn't really allocate memory, there's not anything for our operator delete to really do, but we want it to be there so that we don't call the global operator delete. And a lot of compilers would warn you if you forget to put this step in. Certainly warned me when I tried compiling this. So with those features in place, we can now show the full main function. We can just go ahead and create our UART 0 and display objects with typical new expressions, but those will be calling our class-specific operator new functions here. And then the rest of the code is the same as before, loop forever, try to read a character. If we've received a new character, show it on the 7-segment display. Yeah. If you have a question, I think there are mics, there's a microphone up here. Go ahead and come up and you can ask there.
Okay, sorry about the delay. So you said that you need to construct the object at a specific address. Why not use, for example, the placement new?
Why not use the placement new? I could do that as well. That's an equally valid technique, and I have other versions. I've presented similar material in the past where I've done that. In this case, I just chose to use the class-specific new because I thought it presented an easier interface, something that was a little bit easier to use correctly, harder to use incorrectly.
Okay, I thought there was a special reason. Thank you.
Not particularly. Okay, so with that in place, our program should now be running correctly on our target hardware. But as I said before, we'd like to be able to develop on our target hardware, but also on other systems in some kind of simulated environment, because developing on the target hardware isn't always practical or convenient. For one thing, the hardware may not be available yet. If we're still early in the project, the hardware itself may still be under development. Even if once we have it, still takes time generally to upload the program to that hardware. And if we're trying to do fast edit, compile, test cycles, that's time that we don't necessarily want to spend until we have to. Obviously, we do need to test it on the target hardware eventually, but if we can get the first couple of bugs out on the simulator, so much the better. There's also the fact that there's certain code that's difficult to test on target hardware because it's hard to test error recovery code on the hardware because we can't make the hardware do what we want. We're not in control of it. It does whatever it's going to do. And so if there are parts of the hardware where the documentation says, here's how you do this operation. If it succeeds, it will do this. Otherwise, it will do this other thing. We just, on the target hardware, we just have to wait for the hardware to do the other wrong thing that fails. That's the only way we'll see it. We can't generally cause that to happen. But we can cause that in a simulated environment much more easily. So how can we write one of these simulated environments? So first pass, the versions of UART and seg7 display that I've shown you here implement their interfaces just in terms of the class hardware. If we were just talking about simulating the main program, all we would need to do is write versions of the UART and seg7 display that provide implementations that do similar sorts of things in a way that's appropriate for the simulated environment. So here, for example, I've written a simulated version of the UART class that reads its characters from a file rather than receiving them in from the hardware. And then here is the get function. Can look as simple as that. Again, it's based on how that get function works for iStreams, so no surprise, I can just call that one function right here. And if we're just talking about wanting to be able to create an environment where the main function can run, that might work just fine. But as I mentioned before, this code like this can be non-trivial. Is there a way we can make our simulator also be able to run this code so that we can test this without necessarily having to load it to the target hardware? So we'd like to get something like our UART class, the one that I've been showing you up until now, or something very close to it anyway, running in our simulated environment. So taking this class, how can we make it work on something other than the target hardware? So there are side effects to accessing these registers on the target hardware that we need to take into account. On the hardware, those things happen for us automatically. For example, as I mentioned, when we read from the receive buffer, that automatically clears the RDR flag in the status register. In the simulated environment, we're going to need to write the code to duplicate those effects or produce similar effects when we access our device register members of types like UART. And specifically, we're going to have two different kinds of side effects that we're concerned with. An on-read side effect for dealing with things like reading from the receive buffer, as I just mentioned, and also a write side effect, so that when we write to a control register to do something like enable or disable the UART, that can have the appropriate effects in our simulated environment. And we need to keep in mind, different registers are going to have different side effects here. So we're going to need to write our code, our simulation, in such a way that different device registers can trigger different side effects. So on the target hardware, device register was a type alias for uint32t volatile. In the simulation, what we're going to do is we're going to turn device register into a class type that contains a uint32 volatile. And that's where we're going to store the actual value that the register currently contains. Now, our code, like UART get, reads from the device registers as if they were uint32Ts, which on the target hardware they basically were. But how can we make this work on our simulator? What we need to do is we need to write our device register class with a conversion operator that will let us implicitly convert a value of type device register into a value of type uint32t. So a conversion operator function, we don't see these that often. They don't come up. There are not a lot of situations where I recommend using these, but I think that this is a reasonable one. Function just called operator, name of the type, stood uint32t, returns an object of the appropriate type. And in this case, it's also going to give us a location where we plant the trigger for our onRead side effect. Because whenever we try to use a device register as if it was the underlying uint32t, that's the point at which we're reading the value from the register. So once that function is in place, uart_get will behave in the simulated environment as if I'd written code kind of like this, where I was explicitly calling the conversion operator. You wouldn't normally write code like this. This is just meant to help you visualize exactly what's going on in these situations. Similarly, the disable and enable functions on the UART write to a device register as if it was a uint32t. So these two functions both write to the ucon register. How can we get that to work the same way in our simulated environment? We can overload an operator equals function for device register that takes in a value of the type that we're expecting and carries out the appropriate actions on the device register. So here we have an operator equal that accepts in a value of type uint32t, assigns that value to the internal storage within our simulated device register, and then triggers the onWrite side effect associated with writing to that location. Now, normally, an assignment operator like this would return the thing that was assigned to. I've chosen to make this version of the function return void instead. Usually, I think it's a good idea to mimic the behavior of the built-in operators as closely as possible. But if we could do that, but if we did that here, we'd be able to use this function for reading from the device register as well. And I didn't want to get into that complication. So here I had it return void. Since we often operate on our device registers using bitwise operations, I've also written the device register class to support and equals and or equals. Now these involve both reading and writing, so they're going to trigger both side effects. So the and equals function triggers the read effect, goes ahead and actually does the bitwise operation on the internal value, and then triggers the resulting write effect. Similarly, the or equals operation triggers the read effect, does the bitwise operation, triggers the write effect. Now, as I mentioned, different registers are going to need to support different side effects in this case. So ordinarily, there are lots of different ways that we might choose to solve this problem. But in this case, we're constrained because we want our existing definition of the UART class to work in this simulated environment without modification. So our UART class looked like this. So all of our device registers are declared as the same type. So we're not going to be able to use something like virtual functions or template type, or by templatizing these things to provide different behaviors for our different device registers. They've all got to be based on the same type. And moreover, we've already written the UART constructor that we want to use. It doesn't have any member initializers in it. It's default constructing all of those device registers. So we also can't rely on that constructor to provide information to the individual device registers about what their side effects are supposed to be. So, okay, we can't use the type, we can't use the constructor. What can we use? Well, let's try working with the location of the register. I mean, that's how the target hardware does it, right? These registers mean specific things to the hardware based on their location. So, we'll represent a side effect as a pointer to a function that takes in a uint32, the value of the register that we're operating on. Doesn't need to return anything, has side effects. Doesn't have a return value. Now, I'm showing it here with using a pointer to a function. Alternatively, you could use something like a stud function if you wanted to. Might provide additional flexibility. If you're familiar with how stud function works, that would give you the ability to use something to write the handler as something like, say, a lambda function. If not, you can stick with a pointer to a function like this, like I'm showing here. And then for each device register, we're going to have two effect handlers. So there's a single object, there's an object type effect handlers that contains an on-read handler and an on-write handler. And we're going to be able to associate, we want to be able to associate these with our device registers. So again, going back to the example I've used so far, reading from the receive buffer, we want that to trigger a side effect that clears the read data ready bit in the status register. So the handler for that might look something like this. The first approximation, we want a function that's going to go to the status register and clear the RDR bit there. So, and when we have that handler in place, then looking back at our conversion operator, then we want our conversion operator's code will look something like this, where it will, each time we read from the register, we'll check to see, does that register have a read handler associated with it? If it does, go ahead and call that, passing in the value that we're about to read out before we actually do the read itself. So how will we associate these device registers with their effect handlers? For this, there are lots of ways we could do that. In this case, I'm going to use a map to do the association. So I'm going to create a map as a static data member of my device register type and have a static member function, set register effects, that takes in the address of a register and the set of handlers for that register and enters that into our map. Now, on real hardware, I wouldn't want to do something like this. I often have quite severe memory restrictions on my target hardware that I need to abide by. And so I may very well not be able to allocate dynamic memory the way that the map is going to in this case. But the map is unique to my simulation. It's not something that is ever going to be run on the target hardware. So I have a little bit more flexibility in terms of how I can go ahead and implement the simulated, the back end of the simulation here. So don't have to deal with quite those same limitations. All right, well, now we're back to a situation where we need the registers in our UARTs to be located at specific memory locations, because that we're basing their side effects, the side effects that we want them to have, on their locations in memory. Well, fortunately, we've already solved that problem using the class-specific operator new. So what we need is, for the simulated environment, we just need a slightly different version of the operator new function for our UART that will use an appropriate location where that we can use to associate with our side effects. Now, there are actually a number of pieces to writing the simulated UART, as we'll see. So very quickly, as I was putting this together, I realized that I wanted to be able to keep that separate from the main UART code. And the way that I chose to do that was by creating a base class called basic sim UART, taking the standard library convention of using basic as the generic name for something, although in this case it's a base class, not a template. And I put the operator new and delete functions that are specific to the simulator in there. And then my main UART class inherits from the simulator, from the simulated UART, and takes those functions, makes them available as public members here. Realizing I'm missing the keyword public there. I'll make sure that that's fixed in the slides that get posted. So as long as we're doing that, probably makes sense to do the same kind of thing for the code that's specific to the actual target hardware. So I've created a basic E7T UART that defines its own versions of those functions. And on the target hardware, my UART type will derive from that kind of basic UART and make use of those functions. So altogether, with a little conditional compilation here, the code winds up looking something like this. In my simulated environment, I have a type that isolates all of the pieces that I need for my simulated UART to work. On the target platform, I've got a type that isolates the things specific to the target platform's version of the UART. The rest of the UART code is shared between the two. It just inherits from a different base class in each of these situations. Otherwise, the code remains exactly the same. So, to basic sim UART, we need a few more pieces to really make this simulator work. So I'm going to add 2 new static data members here. Sim hardware is an array of device registers, and this is where we're going to construct the UART. This is going to be the location at which our UART will be positioned in the simulator. So, and it needs to be the same size as, well, at least the size of a UART, but no reason to make it bigger than that. We'll also have another array containing the effect handlers associated with each one of those registers. So, and now when we, our operator new for the simulated UART, it will return the position, it will return the location of sim hardware as the place to create our UART object. But it will also go ahead and set up the side effects for the registers as it does so. Now, this is one way of doing it. There are lots of different ways that I can imagine solving this same problem. At least one of my reviewers for this talk looked at this and he said, I'd prefer if you did it a different way. I experimented with a couple of different things. While I found other ways to do this, I didn't find any that were quite as succinct. So I stuck with this for this talk. But again, I'm not trying to give you something that you have to follow to the letter here. I expect that you're going to have to do real work to adapt this to your own hardware and your own circumstances. It's meant to be more of a general model that you can follow. All right. And then our handler functions. We will implement those as private static member functions of the simulated UART type. So here I've added two new functions down here at the bottom, one for handling a read from the receive buffer, one for handling a write to the control register here. And then when we define our sim handlers array in our CPP file, or CppM file if you have modules available, we go ahead and insert the handler, set up the handlers in that array.
We have an online question.
Yep.
I have not touched embedded development in a long while, so sorry if this is obvious to everyone else here. But if you're using conditional compilation to have UART derived from one of the two base classes, why is inheritance used? Why not make it a...
Sorry, I missed. Can you repeat the question?
Sure. If we are using conditional compilation to have the UART derived from one of the two base classes, why is inheritance used? Why not make it a class template?
Why not make it a class template? You could do that as well. I think that's a perfectly reasonable way of doing things. I thought that for the sake of what I was doing right here, I thought that using inheritance was a little bit more convenient, but I think it's a matter of degrees. If you think that if templates would suit your particular use case better, by all means, go ahead and use that. Okay, so as private member functions, our side effect handlers can access the registers of the basic sim UART. So they can see the sim hardware array, which they need because they're going to be able, because when I do something like read from the receive buffer, I need to go ahead and clear the RDR bit in my status register. So here's a slightly revised attempt at writing that side effect handler. But this is still not the final version, and you may see a problem with it. We've done our job too well. ustat is a device register object in our simulator. We've now got it, we're now applying the and equals binary operation to that register, which will trigger the read and write side effects. So we need some way for our side effect handlers to be able to modify the values in our device registers without triggering additional side effects. So how can we go about doing that? Well, again, there are lots of ways that I think we could do this. We could add some member functions to device register that provide a backdoor in which we could, through which we could make these kinds of changes or read from the value without triggering these side effects. That said, I wasn't really comfortable making these public members of device register. That exposes them to the whole application. Really prefer to avoid doing something like that, even though most of my application shouldn't try and call these because those same functions wouldn't exist on the target hardware. So a better alternative, I thought, was what I can do is I can make them protected member functions of my device register. So they're not actually accessible to the outside world. And then I can have a derived class sim device register, specifically for my simulated device registers, that then promote those functions to public here. And notice I have a static assert down there at the bottom to make sure that these two types really are layout compatible, so they'll be the same size here, which means that in my basic sim UART type, I can go ahead and change that array, the sim hardware array, into being an array of these sim device registers that have this backdoor available. And my side effect handlers will see sim device registers. And they will have access to functions like the backdoor bit and there that I'm using to bypass triggering additional side effects when I clear the RDR flag in the status register. But the code in the rest of the UART just sees plain device registers that don't provide any backdoors, at least no public ones. And as long as device register and sim device register are layout compatible, it should be perfectly fine. And I asserted that that was the case back here. Fortunately, there's a type trait introduced in, I believe, C++ 20 that can solve that problem for me. So that brings, with that all in place, now I'm set up, I should be able to write whatever side effect handlers I might want to make my simulation do whatever it is that I need it to do. So in this example, I've written the handler for writing to the control register so that if it detects that I'm enabling the UART, it should spawn a thread that will go off and essentially simulate receiving an A character from the outside world via the UART once a second. And we'll do that by storing an A into the receive buffer, and setting the RDR bit in the status register. And with that in place, I should be able to, my main program should then be able to run, and it should see 100 A's go by and be received and be printed out to my simulated version of the 7-segment display. That brings me to the end there. So if anyone has any questions, I'm happy to go ahead and take those now.
Hi. When you were starting the talk, I thought you were going to go in a different direction, and I'm wondering why you didn't.
Okay.
When you have the simulated device uint, I was thinking you were going to do something like, okay, this is an empty struct, and it will actually be at location 0 or 4 or 8, because I will not change the new. And then in the function, all the functions that you overload, it looks at its own address and then goes to some different outside global buffer to get all the data and do all the decisions. Instead of having different news and doing all of that. Have you considered doing something like that? Or why you can't do something like that?
I'm not sure I think there's an interesting idea there, but I'm having a little difficulty picturing it just on the spot here. Yeah. So if you want to come up after the and jot something down or something like that, I think I can comment on it in a little bit more detail. But I think that there are lots of different ways that you could accomplish a goal like this.
Okay, we can talk about it later.
Yeah, I guess I would say that I didn't want to rely on the memory space on the. I didn't want to make too many assumptions about the memory space of the desktop running the simulation.
Right. That makes sense.
So we have one more online question by Dan Green. Do you have any thoughts or tricks for simulating interrupts, especially preemption?
Do I have any thoughts about simulating preemptive
Interrupts?
interrupts?
Yes.
You could certainly do something like that. I admit that I have not tried to extend this particular code to the point of actually being able to simulating an interrupt controller in this kind of using this system. I don't see any reason why you couldn't, and I think my first instinct would be to do something similar to what I was doing here, where I would be having some thread that triggers interrupt conditions. Now, here, this thread, I set it up so that it was using the backdoor write function so that it could, because I was using a polling approach of checking the current state of the UART to keep things relatively simple for the purposes of this talk. But the UART hardware on this board does support interrupt driving it instead. And I think that what I might do in that situation is do something like this and then write and then additionally have a step of writing to a bit in the whatever I'm using as my interrupt controller that would then trigger the actual, that would then be an actual write to that location, triggering the side effect of setting the interrupt off. I think it's doable, but it just has a lot of moving pieces to it. I'm happy to discuss that further by email or something like that. I gave my email, ben@saxonassociates.com. It's in the beginning of the slides. If you want to follow up with that, I'm happy to do so.
Hey there. Would you recommend this approach for more complicated peripherals like CAN, for example, that have hundreds and hundreds of bit fields or registers, and also in some cases branch across multiple shared registers from, like, say, a CAN 1 and CAN 3 share registers together?
Mm-hmm. Yeah, that's. I admit that that's a bit of a different situation there. And are you in the situation when you're talking about something that consists of hundreds of registers like that? Are you actually writing the code yourself? I mean, I was sort of assuming up to this point that my UART type was written by one of us, but in your case, is it actually generated by something that looks at the hardware spec?
Yes. Yeah.
Mm-hmm. Yeah, I can imagine that might be tricky. This is. I haven't tried, but I think that it would be difficult to adapt this system to bit fields. I can't think of off the top of my head a way that I would, well, here I've made sure that my registers had the same layout as they would on the target hardware, but I suppose that they don't have to. The code for something like UART get simply relies on the fields having the same names as they would on the target platform. It's back here somewhere, I'm sure. So I suppose that there's nothing that requires that BR div there, for example, actually have the same shape. If that were a bit field, it could be a full object in this kind of simulated environment. Would I recommend doing it? My tendency would be to say, I was aiming this talk primarily at an audience that had a relatively that was looking for a way to accomplish this goal without investing a lot of time in tools and frameworks and things like that. For something like the situation that you're describing, I can imagine that some kind of a more framework-based solution or something that was a more of a dedicated simulator program might work better for that application. But I haven't tried applying it to something like that. I don't know of a reason why it couldn't work.
Sure. Well, thank you.
Just a reminder, we only have 3 minutes, so.
Very much related to the previous question, any comments on the trade-offs between the complexity of modeling the hardware devices versus just being able to test them and writing a more simulator-based approach for the simulations?
I'm not sure I follow.
Like, before we talked about just like a simulated UART that could provide bytes but not necessarily match flag for flag operation on the hardware. Do you have any comments on the trade-offs between trying to model an existing system, which might have its own hardware bugs, for example, versus just using a less hardware analogous simulation?
That's an interesting thing. I mean, when you say hardware bugs, especially, that's a real. When I would, before I did my current job, I worked for a company called Born Industries, and I remember that the hardware engineer there pointing out to me as I was going through writing a device driver for some chip, pointing out to me the section in the documentation labeled lesser known features, which was, by which they meant, these are the bugs that we couldn't fix. And we've sold enough of the product that they haven't been a serious problem. We're gonna just leave them in and label them as lesser known features. If you're actually depending on something like that, then, I mean, I guess for an approach like this, the simulator would have to replicate those things as well. And that could be a tall order, I'll admit, because if your hardware documentation is anything like mine, sometimes it says if you don't do this, this bad thing will occur. But other times it will say, just do this, and then if you did it right, this successful thing should occur. And they don't say anything about what will happen if you get it wrong. So that is definitely a tricky situation for something like this, and that is a limitation of a simulated approach here. I think that for something like, if you're talking about real stepping outside of the documented behavior and into things like how does it respond to error codes or other things like that, that might be, you might find that that's something where this simulator approach might not work quite as well for you.
Even looking outside the errors, though, like any comments on the trade-offs between the complexity of modeling the device at a more hardware similar level versus not?
Yeah, I mean, okay, so you're talking about back here, I'd presented the idea of simulating something like this. You're
Yeah.
talking about? I think it's a time investment question. It depends on. I mentioned this code is non-trivial. It's not that complicated in this situation. I wanted for this talk, I wanted to use something that was a relatively simple example so that I didn't have to fill up pages and pages of stuff. But yeah, for something like this, it might be that the investment of time to create the more complex simulator that I've shown here is not, isn't justified in terms of testing a piece of code that's this big to work. But yeah, it's something that I think it's a trade-off I would have to look at on a case-by-case basis. I think we're at the end of our time, but I'm happy to continue answering questions afterwards. So in any case, thank you all for coming. I hope you guys find this useful.